What is the size of an electron? In any modern physics textbook, you'll read that the electron's size is considered to be zero. This is one of those ideas that seems almost incomprehensibly strange. We know the electron is a completely material object. It has mass, electric charge, energy, momentum, and even angular momentum, which we also call spin. So how can it have no size? It's natural to suspect that physicists might be overcomplicating things here, and that the electron must have some kind of size after all. This is exactly what we'll discuss in today's video. Whether the electron actually has a size, what it might be, and how it's defined in modern physics. When asking about the true value of a property for an object in modern physics, the first thing we need to clarify is what we mean by true. This becomes especially tricky when dealing with the sizes of quantum mechanical objects, which we habitually call particles, even though they're not really particles in the classical sense, like tiny solid spheres. If elementary particles were truly solid spheres, or any other classical objects, physics would be much simpler and more intuitive. The radius of a solid sphere unequivocally defines the volume of space it occupies. All space could then be divided into two regions, one where a probing stick touches the sphere and one where it doesn't. By probing enough and analyzing the results, we could precisely determine the size of our sphere. With quantum mechanical objects, i.e. subatomic particles, things are fundamentally different. No matter how small or precise our probing stick is, we can never identify a region where the particle definitely exists or definitely does not. At best, we can determine the probability of finding the particle within a specific region. However, no region of space can ever be identified with 100% certainty as containing the particle or completely excluding it. Consequently, the classical concept of size, which applies to any respectable material object, is inapplicable in quantum mechanics. Physicists, therefore, generally consider discussions about the true sizes of particles meaningless. Instead, they usually talk about the so-called effective sizes of particles, the sizes that classical solid spheres would need to have to behave like quantum mechanical objects in certain contexts. For instance, when physicists mention the radius of a proton, they usually mean its charge radius, the radius of a sphere with the same charge as a proton that would behave similarly in electromagnetic interactions. This charge radius is approximately 8.8 by 10 to the power of minus 16 meters, determined through highly precise measurements of the hydrogen atom spectrum, where the nucleus consists of a single proton. By using quantum electrodynamics equations, we can calculate the expected spectrum of such an atom under the assumption that the proton is a point-like object. Experimentally, however, slightly different values are observed, partly due to the proton's finite size. By measuring these differences, we can estimate the proton's effective charge radius. For simplicity, this charge radius is often referred to as the proton radius. Though strictly speaking, that might be misleading because it suggests that the proton is a solid sphere with a definite radius, which it is not. Can we define an analogous charge radius for the electron? Not only can we, but physicists have attempted to do so multiple times. The first person to estimate the electron's radius was quite logically its discoverer, J.J. Thomson. Thomson essentially used dimensional analysis, constructing a formula that results in a value with the dimension of length from parameters describing the electron and various fundamental constants. Thomson's formula included the Coulomb constant, the electron's charge, me, its mass, and c, the speed of light. Substituting the known values, he obtained a radius of approximately 2.8 by 10 to the power of minus 15 meters, of the order that physicists of the late 19th and early 20th centuries might have expected for the electron's size. Later, Thomson's formula was given a physical interpretation. For example, Hendrik Lorentz proposed the following reasoning. Let's assume that an electron consists of some negatively charged substance with a total charge equal to the electron's charge. The particles of this negatively charged electron matter, whatever they may be, would repel each other electrostatically. To compress them into a sphere of a specific radius, energy would have to be injected into the forming electron. This energy would then remain stored within it, And it is this energy, according to Einstein's famous equation, E equals mc squared, that we perceive as the electron's mass. From there, the reasoning is straightforward. The energy required to compress this charged electron matter with charge EE into a sphere of radius r can be calculated using the formula, where V is the potential of a charge q at a distance r. The charge q can, in turn, be expressed through the charge density of the electron matter multiplied by the volume of the electron sphere. Then, through a simple integration process, we obtain a formula for the energy stored within the electron. The final step is to equate this energy to mc squared and solve for the electron's radius, which essentially yields the same formula as Thomson's, with an additional coefficient of 3/5. This is not surprising since the dimensional analysis method used by Thomson typically provides results accurate to within a dimensionless constant. The coefficient 3/5 arises from the assumption of a uniform charge density distribution, which is by no means guaranteed to be accurate. For simplicity, and because the order of magnitude remains unchanged, it was decided to omit this coefficient. From today's perspective, armed with quantum mechanics, Lorentz's reasoning seems rather naive. Even without invoking quantum mechanics, it's evident that the Thomson-Lorentz formula is likely incorrect. For instance, the same logic could theoretically be applied to determine the radius of a proton, and the result would imply that the proton's radius is smaller than that of the electron, which seems implausible. To this day, there are no solid theoretical approaches for determining the electron's radius, leaving the task entirely to experimentalists. Over the past half-century, numerous experiments have been conducted to shed light on this question. Among the first such attempts were experiments on electron beam scattering on protons. These scattering results showed that if the electron has any radius at all, it must be smaller than 10 to the power of -16 meters, 10 times smaller than the classical radius given by the Thomson-Lorentz formula. However, this was the limit of these measurements' precision. More accurate and sensitive methods were required to determine the actual size, or rather the charge radius, of the electron. One such method involved measuring the so-called Lamb shift in the emission spectra of hydrogen and hydrogen-like atoms, atoms with one electron in the outermost energy level. The quantum mechanical theory of the hydrogen atom, derived from the Dirac equation, allows for fairly accurate predictions of the possible energy levels an electron can occupy in hydrogen-like atoms. However, experimental results showed that these spectra deviate slightly from theoretical predictions. The discrepancies were minuscule. If the energy of the ground state electron in a hydrogen atom is 13.6 electron volts, the shift observed in 1947 by Willis Lamb and Robert Rutherford was just 4 millionths of an electron volt. Nevertheless, even such a tiny deviation, known as the Lamb shift, required an explanation. This explanation was found within the framework of quantum electrodynamics, which was gaining traction at the time. In quantum electrodynamics, electromagnetic interactions are described as the exchange of so-called virtual photons between interacting particles, an idea we discussed in one of our previous videos. However, calculations showed that even in the absence of charged particles, the vacuum itself generates virtual photons. This process, and the concept of virtual particles in general, were also topics we explored in another video. Naturally, the vacuum continues to generate virtual photons even when real particles are present. This effect introduces a small but non-zero correction to the observable electromagnetic interactions, as if the vacuum itself possessed a very weak but non-zero electric field. The process of creating and annihilating virtual particles is purely random. Consequently, the direction and magnitude of this vacuum field are also random. Due to this correction, the energy of an electron in an atom undergoes slight random variations. In a crude semi-classical analogy, where the electron is visualized as orbiting the nucleus like a planet around the sun, this would manifest as the electron jittering on its orbit, which randomly fluctuates in size. This shift is precisely what we observe as the Lamb shift in atoms. The magnitude of the Lamb shift in the electron's energy within an atom should, among other factors, also depend on the electron's size. Roughly speaking, the larger the electron, the more frequently and actively virtual photons would collide with it, altering its energy. Unfortunately, even the most precise measurements to date yield exactly the magnitude of the Lamb shift predicted by the theory for a zero-radius electron, meaning that measuring the Lamb shift has not yet revealed any effective radius for the electron. Another phenomenon that could theoretically help estimate the electron's radius is the so-called gyromagnetic ratio, the relationship between its intrinsic magnetic moment and angular momentum. As early as the beginning of the 20th century, many physicists began suspecting that the electron itself, regardless of its motion in space, possesses a magnetic moment. It was tempting to assume that this is because the electron, being a charged object, rotates around its own axis. In classical mechanics, the ratio of the magnetic moment of a rotating charged body to its angular momentum is described by the following formula, known as the classical gyromagnetic ratio. However, experiments showed that for the electron, the gyromagnetic ratio is twice as large following this formula instead. Dividing the experimentally determined gyromagnetic ratio by the classical one yields the so-called G factor. For classical objects, this factor equals 1. For the electron, it equals 2. For the proton, approximately 5.6. For the neutron, 3.8, and so on. Theoretically, the G factor can be calculated using the same Dirac equation, which predicts a value of precisely 2, or more accurately, -2. However, experimental measurements showed it to be slightly larger, or more precisely, slightly more negative. This deviation is explained once again by the electron's interaction with the vacuum's electromagnetic field, or, equivalently, with virtual photons arising from the vacuum, essentially the same effect. In 1947, Julian Schwinger provided a theoretical estimate of the anomalous G factor for the electron within the framework of quantum electrodynamics, which remarkably matched the experimental value. Its magnitude is expressed by this formula, where alpha is the fine structure constant, a fascinating quantity we've discussed in a dedicated video. Now, if the electron were not a point particle, its gyromagnetic ratio would differ both from the pure plot value of 2 derived by Dirac and from the anomalous value calculated by Schwinger for a point-like electron. By analyzing this deviation, we could potentially estimate the size, or more precisely, the effective radius of the electron in terms of its magnetic moment. Unfortunately, even the most precise measurements have not yet detected any notable differences between the theoretical G factor for a point-like electron and the experimentally determined value. Thus, this attempt to probe the electron's radius has also been unsuccessful. At present, the results of these and other experiments allow us to confidently state that the electron's radius is certainly less than 10 to the power of -21 meters. How much smaller? We don't yet know, as we simply lack sufficiently sensitive instruments to measure such tiny quantities. This is why physicists often say that the electron's radius can be considered zero. It's pointless to discuss an effective radius that produces no detectable effects. Some cutting-edge theories in physics propose their own predictions for the electron's size. String theory, for example, suggests it should be around 10 to the power of -34 meters. However, we can neither confirm nor refute this prediction at present, and likely won't be able to for quite some time. This, incidentally, is one of the major criticisms of string theory. All its specific predictions are essentially untestable, leading some scientists to dismiss it as unscientific. But let's return to the electron's size. There's another way to define an object's size, based on how densely these objects can be packed into a given volume of space. Indeed, if we know that a cubic box with a side length of 1 meter contains exactly 1,000 identical spheres, we can confidently conclude that each sphere has a diameter of 10 centimeters, or a radius of 5 centimeters. If their radius were larger, fewer spheres would fit, and vice versa. What about electrons? Since we consider their size to be zero, shouldn't it theoretically be possible to pack them infinitely densely into a given space? Well, not quite. In reality, there is a limit to the density at which electrons can be packed, determined by the Pauli exclusion principle. This principle prohibits 3 or more electrons in the same quantum state from occupying the same region of space. If we compress a collection of free electrons, essentially an electron gas, Eventually, further compression becomes impossible due to the Pauli exclusion principle. At this point, the electron gas is said to have entered a state of degenerate electron gas, which we've discussed in detail in another video. From this perspective, we can attempt to define the electron size based on the maximum packing density. At room temperature, for instance, the state of degeneracy is reached at an electron concentration of about 6 by 10 to the power of 28 electrons per cubic meter. Using our sphere packing analogy, this would suggest an electron radius of roughly 10 to the power of minus 10 meters. Is this a result? Yes, but a questionable one. After all, 10 to the power of minus 10 meters is the approximate size of atoms, not even atomic nuclei, but whole atoms, each of which contains dozens of electrons. This discrepancy arises because electrons within an atom occupy different states, existing at various energy levels and sublevels, whereas the Pauli exclusion principle only applies to electrons in the same state. There's no contradiction here, but it does raise questions about the validity of this approach to defining the electron's size. Furthermore, the concentration of electrons at which degeneracy occurs depends on temperature. For example, at a temperature of 1 million Kelvin, the concentration can reach about 10 to the power of 30 electrons per cubic meter. In this case, the electron's radius would be about 10 to the power of minus 11 meters, 10 times smaller. However, this seems odd. We tend to think of an object's size as an inherent characteristic, independent of the system it belongs to. Consequently, the electron's radius shouldn't depend on the temperature of the electron gas. How can it be that the electron is small enough to show no detectable size in the most precise experiments, yet large enough to behave as described? This apparent contradiction arises because we're attempting to apply the classical concept of size to the quantum world of subatomic particles, where laws and phenomena unfamiliar in everyday life dominate. As mentioned at the start of the video, determining the true size of the electron is challenging because it's difficult to define what true even means in the quantum realm. If you found this video interesting, I kindly invite you to support our channel by becoming a sponsor on YouTube, Boosty, or Patreon. Thanks to the support of our esteemed sponsors, our channel continues to produce new and exciting content for all our viewers. Thank you all, and see you next time.